Hello guys, welcome to my next class of inner product space. In this class, we are going to study for orthonormal set. Before I'm going to start orthonormal set, I'm going to recall orthogonal set. Now you already know that when we say that the given set of vector in an inner product space is orthogonal set, then inner product of each and every vector must be equal to 0. Inner product of v1 comma v2 equal to 0. Inner product of v2 comma v3 0 means inner product of mutual vectors must be a 0. Then we say that is orthogonal set. Suppose that orthogonal set is a non-zero, then you already know that is there. We already derived in the previous video. They are linearly independent and also span the corresponding inner product space. Then we say that that's a orthogonal basis for the corresponding inner product space. Now, in all, we consider some problem. Whenever you want to verify whether the given set of vectors are orthogonal basis, it is enough to verify that the given set of vectors are non-zero orthogonal set. Then immediately from that result we say that they are linearly independent and also span the inner product space. Then we say that the corresponding non-zero vectors are orthogonal basis. Similarly, now we are consider orthonormal set. The orthonormal set is nothing but extension of orthogonal set. A set of non-zero vectors, say S is equal to v1, v2, etc. v, and they having n vectors in an inner product space V is a orthonormal set if every vector in S has magnitude 1 and the set of vectors are mutually orthogonal. Means then length of each of the vector of vectors in S must be 1 and also the inner product of the mutually vectors are nothing but orthogonal. That is, combining these two conditions, that is inner product of vi comma vj is 0 for I is not equal to j, equal to 1 for I is equal to j for every I and j. Then we say that is a orthonormal set. Orthonormal set is a orthogonal set, but orthogonal set is need not be a orthonormal because then the difference between orthogonal set to orthonormal, in orthogonal only we are expecting inner product of the mutual vectors are orthogonal. But along with that, in orthonormal set, each and every vector the length must be 1. This is the difference between orthonormal and orthogonal sets. Okay, a basis B of an inner product space V is called an orthonormal basis if B is also an orthonormal set. Means if we want to verify whether the given set is a orthonormal basis, it is enough to verify that the given set is a non-zero orthonormal set. And then just now I began, before going to start orthonormal set, I told what's the meaning of orthogonal basis. Here, if you want to verify whether the given set of vectors are orthonormal basis, it is enough to verify that whether the given set is a non-zero vectors and also is a orthonormal set. Is orthonormal set means orthonormal set is a orthogonal set, is a non-zero orthogonal set. From the one of the result, every non-zero orthogonal set is a linearly independent and span the inner product space, therefore is a orthogonal basis, therefore is a orthonormal basis. Keep in mind, if we want to verify whether is an orthonormal basis, means it is enough to verify that whether the given set is a non-zero orthonormal set. I think is clear everyone. I'm moving to the next step. That step is actually to verify some problems. Show that the following set is an orthonormal basis of Euclidean space with dimension is 3. It is enough to show that this set is a non-zero orthonormal set. Yeah, clearly v1, v2, v3, these are the non-zero vectors, fine. First, I have to show that three vectors are mutually orthogonal. This mutually orthogonal means what actually? I have to take inner product of v1 comma v2, v1 dot v2. Then you take the inner dot product from these two. You know that is already I solved some problems in previous cases. Then we get inner product of v1 v2, inner product of v2 v3, and then inner product of v1 v3 in all the cases must be 0, means inner product of mutual vectors must be 0. Therefore is orthogonal set. Further step, I want to verify length of the each of the vector must be 1. The length of the each of the vector is 1, means I have to find out norm of v1. What's the norm of v1? Square root of inner product of v1 comma v1. You take that s value, this is my v1, square of this, what we get, r plus r 1. Similarly, you take norm of v2, norm of v3. Root of inner product of v1, v2, v2 is nothing but v2 dot v2, find out, we get 1. And inner product of v3, v3, that gives rise 1. Therefore, this shows that each and every vectors are non-zero, and also mutual vectors are inner product must be 0, and length of the each of the vector must be what actually? Length of each of the vector must be what? 1. Length is 1. Therefore, the given set S is an orthonormal set. We know that non-zero orthogonal set is a basis of Euclidean basis of Euclidean space R3. Thus, R is an orthonormal basis for R3. Keep in mind, if you want to verify whether it's orthonormal basis or not, it is enough to verify that whether the given set of vectors are non-zero orthonormal set. Are you clear? Orthonormal set means first you have to verify that inner product of each of the mutual vectors must be 0, that is orthogonal set, and then verify that length of the each of the vector must be 1. Next, in P3 of x with the inner product, this is a polynomial, they are having a 3 terms, the polynomial up to degree 2. Constant term is also is in P3 of x. Up to linear also P3 of x. Maximum we are expecting P3 having the degree of x is 2. This is a polynomial degree 2. With the inner product space, inner product of P comma Q is nothing but A0 B0 plus A1 B1 plus A2 B2. Then show that the standard basis P is equal to 1 comma x square is orthonormal. It's not given in any textbook I saw in one of article. Therefore, why don't I discuss this type of problem? Now, they given standard basis for polynomial. P3 means polynomial degree 2. Standard basis are 1, x and x square is orthonormal. It is enough to verify. I have to take v1, v2, v3. For this is v1, this is v2, v3. v1 can be written as 1 plus 0 into x, 0 into x square. v2 can be written as 0 plus 1 into x plus 0 into x square. Like that, v3 is nothing but 0 plus 0 plus 0 into x plus 1 into x square. Find out inner product of v1, v2. v1, v2 definitely we get 0. v1, v3 also 0. You just try to, you know how to calculate inner product. If they given inner product of this A0, B0 means 1 into 0 plus 0 into 0, 1 plus 0 into 0. Use this. And then V1, V3 means these are the A0, A0, A1, A2. This is nothing but B0, B1, B2. Then 1 into 0 plus 0 into 0 plus 0 into 1. Similarly, to find out V2, V3. 0 into 0 plus 1 into, take the quotient of constant multiplied with quotient of x, so multiplied with quotient of x square, that's all. Find out length of the each of the vector. Root of inner product of v1 comma v2 is nothing, v1 comma v1 is nothing but root of 1 square plus 0 square plus 0 square is 1. Norm of v2 means root of inner product of v2, v2 means what? 0 square plus 1 square plus 0 square, we get 1. Similarly, v3 also we get 1. Therefore, B is a orthonormal set. Therefore, it's orthonormal set. Therefore, it's a orthonormal basis for the inner product space P3 of x. And then I'm considering another one problem. Let you having, so up to that we are taken in the row, row vector. Here I taken column vector because David Seeley, all the problem they discuss based on column vector. Yeah, they given u1, u2 in the form of column vector. Then you show that the set vector u1 comma u2 is an orthonormal basis for our Euclidean space with dimension 2. Yeah, they return in the column, that's all. It is enough to show that this vector set of vectors u comma u1 comma u2 are non-zero orthonormal set. First we have to show that the inner product between mutual inner product must be 0. Inner product of u1 comma u2 means u1 dot u2. Definitely we get 0. You know already familiar with that, how to find out inner dot product. Yeah, and next you have to find out length of the each of the vector. Inner product of u1 comma u1, inner product of u2 comma u2. Yes, you have to calculate. In both the case we get 1. Therefore, the vectors, your set of vectors u1 comma u2 is a non-zero orthonormal set. You know why I use non-zero? Because clearly say that u1 and u2 are non-zero. After that, what we are going to do here, yeah, orthonormal set. We know that non-zero orthogonal set is a basis for Euclidean space with dimension 2. Thus, u1, u2 is also the set of vectors is a orthonormal basis for Euclidean space with the dimension 2. Now, once again, I am telling that if you want to verify orthonormal basis, it is enough to verify that is orthonormal set. If you want to verify is orthogonal basis, means it is enough to verify is a orthogonal non-zero orthogonal set. There also non-zero orthonormal set. Yeah, I've considered some two problems once again for projection. This orthogonal projection they given in the question paper for this problem. Okay, yeah. If y equals, they given again in the column because this problem they given in David Sele 7 6 and u is 4 2. Find the orthogonal projection of y onto u. I have to find out proj of y on u and the orthogonal set I want to find out. Yeah, first you know that we discussed in my previous video how to find out projection, orthogonal projection. We know that proj of, they asking y on u is nothing but y cap is nothing but inner product of y comma u divided by inner product of u into u into u. This is we get from the definition of orthogonal projection. The next is first you find out inner product of y comma u. Y dot u is nothing but 7 into 4 plus 6 into 2. Simplify that we get 40. Similarly, I have to find out inner product of u comma u. Now, for inner product of u comma u is nothing but u dot u is 4 square plus 2 square. Simplify that we get 20. You substitute in orthogonal projection of y onto u is nothing but 40 divided by 20 of u. U is column wise, the vector is 4 2. Then we get to take it to inside. We get this is a scalar 8 and 4. This is my projection, orthogonal projection of y onto u. Next, I want to find out orthogonal set. You already know that I find out y minus y cap. This is nothing but complement of u. Right? Y minus y cap. What is my y? 7 6. Y cap is 8 4. Now simplify that. We get this is minus 1 and 2. You know how to simplify. You have to subtract the corresponding component. Again we get a column vector. Then observe, you find out inner product of y minus y cap comma u because this is a complement of u. Complement of u means suppose you take inner product of these two vectors y minus y cap and u must be 0. Yeah, take dot product 1 minus 1 2 and u is what actually 4 and 2. Then take a dot product, we get 0. Then we say that y minus y cap is nothing but complement of u. Then they are asking orthogonal set. What is my orthogonal set? The required orthogonal set is y minus y cap and u r. You write the vector. What's a vector of y minus y cap? Minus 1, 2. And what's a u vector is 4 and 2. Keep in mind they are asking orthogonal set means the two vectors are inner product must be 0. Then we say that these two vectors comes in orthogonal set. The orthogonal set having the vectors are y minus y cap and u, or you write the values of y minus y cap and u. This is a way to write the orthogonal set. They allotted for this is 6 marks. Easy to score the marks for this. Next, moving to the next problem. This problem is not given anywhere but is given in the David Sele. Suppose they are going to ask how to do it. Yeah, let u1 is equal to 2, 5 minus 1 and u2 is minus 2, 1, 1 and y is 1, 2, 3. Verify the vectors, set of vectors u1, comma u2 is an orthogonal basis for w, where w is a span of u1, comma u2. Write y as the sum of the vectors in W and a vector orthogonal to W. Yeah. First you have to verify is a orthogonal basis. It is enough to verify that it must be a what about orthogonal set, non-zero orthogonal set. Clearly u1, u2 are non-zero vectors. And next you find out inner product of u1, comma u2. Then u1 dot u2 definitely we get 0. Then we say that the vectors, set of vectors u1, comma u2 are non-zero orthogonal set. We know that non-zero orthogonal set is a basis. Thus, if the vectors u1, comma u2 is orthogonal basis for w is a span of w u1, comma u2. Therefore, W is a orthogonal basis. Yeah. Then next is I want to find out this set of vectors is a orthogonal basis for W. Okay, fine. Next, they want to find out, write y as the sum of the vectors in W. Sum of the vectors in W means y can be written as linear combination of vectors in W. What are the vectors you have in the W? W is having a vectors of U1 and U2. You already know that W is a orthogonal basis. You recall in the previous video, suppose you forgotten, you please go back to my second video, maybe third video. There I derive one result. Whenever talking about is orthogonal basis, suppose choose any vector in vector space that can be written as linear combination of vectors of u1 and u2, where y means y can be written as c1 u1 plus c2 u2. What's a formula for c1 and c2? Ci equal to inner product of y comma ui divided by inner product of ui into ui comma ui into ui. Yeah, I think it's clear. Using this formula only I have to find out C1, C2. Then only is possible I have to express y in terms of the linear combination of u1, u2. They taken already you already proved that is orthogonal basis. I want to express y in terms of w means y can be written as linear combination of u1 and u2. But keep in mind how to find out C1, C2. This is a formula. Why? Because it's an orthogonal basis. We already derived, I proved in my previous videos. Yeah, from this formula, I have to find out C1, C2. First, you find out inner product of which value y comma u1. 1 into 2. Then you know how to find out y dot u1 you calculate, and similarly you calculate y dot u2. And also you inner product of u1 means u1 dot u1, and also calculate u2 inner product of u2 comma u2. You know that u1 dot u2 dot u2 you have to calculate. After that you have to substitute the values of c1 and c2. Then finally we get y in terms of the linear combination. This is u1 and this is u2. What is c1 is 3 by 10. What is my c2 is 1 by 10. Yeah, this is a way to express y in terms of w. Next they are asking another one question write y as the sum of the vectors in W and a vector orthogonal to W. That vector is orthogonal to W. Now here we are express y in terms of the linear combination of u1, u2, where c1 is 3 by 10, c2 is 1 by 2. Suppose you simplify this, we get y cap, projection of y onto W. This give rise what? Projection of y, please try to understand, projection of y onto W. Suppose you simplify this linear combination of u1, u2 with c1, c2 value substitute. Now simplify that gives us y cap. Y cap is nothing but projection of y onto W. Then that implies, now I have to calculate y minus y cap. That is a complement of the orthogonal. Y minus y cap is y, you know that. Y cap, just now I told, after the simplification of linear combination of u1, u2, after you substitute the value of c1, c2, we get y cap. Y cap is nothing but projection of y onto w, because w having u1 and u2. Okay. The next is, I think is clear. This is a projection of u, the not of see sum of these two terms, right? This is nothing but projection of y onto w. W having how many vectors? u1 and u2. That's why we get two terms. Then y minus y cap, you calculate it. Once you calculate it, this must be inner product of this value with u1. Inner product of y minus y cap with u2 must be definitely 0, because this is a complement of w, y minus y cap, because projection of y cap on w are calculated. Therefore, y minus y cap is a complement of w. W having what are the vectors? u1 and u2. Therefore, this y minus y cap dot u1 must be 0, y minus y cap dot u2 must be 0. Yes, then I to express in terms of the orthogonal, what they are asking, orthogonal to w. Therefore, y can be written as y cap plus y minus y cap. Add and subtract by y cap. What we get? Y cap plus y minus y. We substitute y cap value this. Y minus y cap is this. If we want to add these two, definitely we get y value. Add that, we get y. This is nothing but give rise y as the vector of w, orthogonal of w. Yeah, first I have to express y in terms of the in terms of w means in terms of u1 and u2. You simplify that, we get y cap. Y cap is nothing but projection of y onto w. But keep in mind, w is not having only one vector, is having two vectors. Therefore, we get sum of two terms. Sum of two terms. Please try to understand. Once you substitute this, we get one term. This is a substitute to C2, we get another term. Therefore, that gives us y cap. Y cap is nothing but projection of u, orthogonal projection of y on w. And then you calculate y minus y cap. This is a complement of w, definitely. Then y can be written as y cap plus y minus y cap. Then add these two, definitely we get y. This is nothing but the y can be expressed in terms of orthogonal of w. Now, it's not yet given any question paper. Suppose they are going to ask how to do it. That's why I'm explained. You please go through calmly, neatly. Suppose it's not clear, you pause and then go to 2 to 3 times my video. Then try to understand that. Yeah. Once again, I'm telling that y cap, how we get here? Y cap is nothing but projection of y on w. But w is having two vectors, u1 and u2. Therefore, what's the formula? Inner product of y comma u1 by inner product of u1 plus inner product of y comma u2 divided by inner product of u2 into u2. Yes, that's why I written y cap. Yeah. Thank you very much for listening. I'll come and meet you in the next class, Gram schematic method. Okay. Bye. See you. Take care.